The paper we're diving into today is titled See Less, See Right, Bi-directional Perceptual Shaping for Multimodal Reasoning. And it really cuts straight to the heart of a huge reliability problem in large vision language models. Their inability to truly see and ground answers in fine-grained visual evidence, especially, in complex charts.
Exactly. And the central idea here is something they call bidirectional perceptual shaping, or BiPS. You see, most models struggle with focus. They rely on these heavy external tools at inference time, things like cropping algorithms or bounding box generators to guide their attention.
Right.
BiPS just flips that whole paradigm on its head. It takes perfect ground truth visual cues, which are actually pretty easy to generate programmatically, and it bakes them in as these powerful internal training signals instead.
So it's shaping the model from the inside out. And the mechanism behind this involves two distinct Kullback-Leibler divergence constraints. The first is a consistency constraint. It acts as a kind of positive signal, pulling the model's predictions toward views that preserve the necessary evidence.
While the second is, I think, the really crucial part, a separation constraint. This one acts as a negative regularizer. It actively pushes the model's predictions away from views where the key evidence has been removed. It basically forces the model to learn that the visual signal is indispensable for a correct answer.
And the results really seem to back this up. This perceptual shaping boosted their base model, Qwen 2.5 VL7B, by an impressive average of 8.2% across 8 major benchmarks. That's a huge lift, especially for tasks involving charts and quantitative reasoning.
It really is. It demonstrates that teaching the model where to ground its answer during training is just far more effective than trying to, bolt on perception tools at the last minute.
Okay, so let's unpack that core problem a bit more.
Right.
We all know VLMs are phenomenal at general stuff like describe this scene or what's the main object here. But they just fall apart when the task demands that fine-grained perception, like reading the exact intersection point of two tiny lines on a chart.
That's the perceptual bottleneck, precisely. The model takes in this entire high-resolution image and it kind of gets overwhelmed. And because it can't isolate that subtle, definitive visual evidence, it just defaults to a linguistic shortcut.
So it guesses.
It makes a very educated guess. It might see some related text or use context from the question and generate an answer that sounds plausible, but is totally mismatched with the actual evidence in the image. It's seeing broadly, but it's not seeing right.
And the paper gives a good critique of why the current solutions don't really work. We've all seen this external tool-dependent paradigm. People try to pre-process images by cropping them or asking the model to generate a mask before answering.
Yeah, but those methods have two major technical limitations. First, you've got the problem of shape rigidity. A rectangular crop or a coarse mask, it fails to capture the complex, irregular shape of the actual evidence. Think about trying to trace a specific path in an engineering schematic. A rectangle is useless.
Right. If the evidence is a thin, wavy line or some scattered data points, a bounding box just introduces a ton of noise.
And the second limitation is inference overhead and cascading errors. If you introduce an external tool, you have to run it at test time.
Which adds latency.
It adds latency, which is bad for deployment. And what's worse, if that tool generates a slightly wrong cue, the VLM's final answer is now built on a flawed foundation.
So the BiPS philosophy feels really different here. Instead of asking the model to generate a cue at inference, which is error-prone, they use perfect handcrafted cues to sculpt its internal decision-making during training.
Exactly. They're teaching the VLM to be inherently biased toward seeking out the necessary visual evidence. It's almost like embedding an internal attention policy that's grounded in the actual truth. And this completely bypasses the need for those costly external tools when the model is actually deployed.
So let's get into how they actually manage that policy optimization. They use something called Group Relative Policy Optimization, GRPO, with these two complementary KL divergence constraints. So for our listeners who aren't, knee-deep in reinforcement learning papers every day, what is KL divergence conceptually measuring here?
At a high level, KL divergence is just a way to measure the difference or the distance between two probability distributions. In this context, we're measuring how far the model's prediction policy, its probability over possible answers, is from some target distribution. By minimizing it, you pull the policy toward a target. By maximizing it, you push it away. That's the bidirectional force.
That makes it much clearer. Okay, so let's look at that first force, the positive one, the consistency constraint. What's its primary goal?
The goal of LOCONs is to establish a foundational, sort of coarse-grained focus. You want to make sure the model maintains a consistent prediction even when you remove non-essential distracting parts of the image. So it minimizes the KL divergence between the model's policy on the full original image and its policy on what they call the evidence-preserving view.
So if I'm getting this right, the evidence-preserving view, the IPRESER view, is basically the cheat sheet version of the image. It only shows what's absolutely required to answer the question.
Precisely. If the question is about the value of the green line, the LB view might just be the green line and the axis. Everything else is gone. It acts as a perfect positive guide. It tells the model, hey, your decision should be based only on this stuff. Everything else is just noise.
I saw in the paper they used a little technical trick here, a stop gradient on the IPRES policy. Why was that necessary?
Yeah. That's a crucial detail for stability. If you let both policies update, the target would drift. By applying the stop gradient, the IPRES policy becomes a fixed, stable target. It ensures that the model's main policy is the only one doing the learning, constantly trying to align itself with that perfect, reliable target.
Makes perfect sense. You need a stable beacon to steer toward. But even with this, there's still an escape hatch. The model could just learn to ignore the image entirely and rely on some textual cue in the question. That classic shortcut learning problem.
And that is the exact failure mode BiPS is designed to prevent. Lock-on alone isn't enough to force real grounding. That's where the countersignal comes in. The negative regularization from the separation constraint, lock-on.
Okay, so lock-on is the complete inverse. It maximizes the KL divergence between the prediction on the full image and the prediction on this.
Yeah.
Evidence-ablated view, the libel view.
For the idle view, we take the image and we surgically remove the key decisive pixels needed to answer the question, but we leave all the context, the axes, legends, other data points. So if the question is about an intersection point, the idle view is the chart without the two lines that intersect.
And because the correct answer is now visually impossible to determine from that view, maximizing the difference in predictions forces the VLM to admit that the removed evidence was critical.
Exactly. It actively penalizes the model if it somehow produces the correct answer when the visual evidence for it is missing. This constraint just shatters those text-only shortcuts. The model learns that guessing based on text without visual confirmation leads to a huge penalty. It must look at the data.
Now, to make this work, you need an exceptionally clean data set. You can't just do crude masking.
No, absolutely not. And that's really the unsung hero of this paper, their programmatic data construction pipeline. They use the ECD synthetic chart corpus, which is key because it doesn't just come with images, it comes with the executable rendering code that generated them. Working at the code level gives you semantic control, not just pixel control.
Wow. So you can turn visual elements into variables. You can just delete a line of code to remove a data series instead of trying to draw a messy polygon around it.
That's it. So their pipeline starts with question reformulation. An auxiliary LLM converts open-ended questions into a multiple choice format, which gives you a clean signal for the RL training.
And then stage 2, the difficulty filtering. I thought this was brilliant. They took 50,000 samples and just threw out any question the base model could already answer perfectly every time.
It's such a smart way to build a curriculum. They focus all their training budget on the problems the model is actually struggling with. That's how they got from 50,000 down to about 20,000 really challenging samples.
It just maximizes the value of every single training step. And then we get to the core of it, code editing and counterpart rendering. Right. How did they generate the two views?
For the evidence-preserving view, the system just programmatically deletes all the code segments that are extraneous to the question. If the question is about one subplot, the code for the other two gets stripped out.
And for the evidence-ablated view?
The editing was surgical. They didn't just remove a random part of the image. They removed the line of code that generates the one key decisive piece of data. So for a question about subtracting 2 bars, the idle view might show everything, except for one of those 2 crucial bars. The image looks plausible, but the answer is visually unverifiable.
The quality of those 13,000 final samples must be incredibly high.
Absolutely, and they proved it. They compared this programmatic code editing to a random masking baseline, and the difference was stark. Random masking performed terribly because it generated noisy gradients. It just couldn't provide the clean, reliable signal that BiPS needs to work.
Okay, let's move to the training schedule, because they found that trying to optimize both DAL-Cons and DAL-Lorai at the same time was, well, a recipe for disaster.
It was. It leads to conflicting gradients and instability. You have one force pulling the policy inward and another pushing it outward. If you apply them jointly, you get high variance and it doesn't converge properly.
The solution was this 2-stage, course-defined curriculum. Stage 1 is all about the positive signal. DALCON's just establishing that foundational focus.
And then, once that stable coarse focus is there, stage 2 introduces the negative regularization, DALSA. That sequential order is critical. Their ablation study confirmed that consistency, then separation, dramatically outperformed joint training, or doing it in the reverse order.
So you have to teach it what to look for first and then teach it what to ignore. It can't learn both at once.
Exactly. You give it a stable policy base before you start trying to teach it to avoid all the tricky shortcuts.
And now for the payoff. The performance gains are substantial, especially when you think about the data efficiency here. BiPS Chart 7b, trained on only 13,000 samples, got an average gain of over 7% on its baseline.
And the jumps on chart-specific benchmarks are massive. We're talking a 16.2-point increase on EvoChart, 15.3 points on ChartQO Pro. But what's really crucial is the out-of-domain generalization. Even though it was only trained on synthetic charts, its performance shot up on general benchmarks like MathVista and MMStar.
That's the real proof point, isn't it? It's not just learning to read charts better. It's genuinely improving its fundamental perceptual capacity, which applies everywhere.
And you have to highlight the data efficiency. I mean, for any ML engineer listening, this is huge. BiPS Chart 7b with just 13K samples beats specialized chart models that were trained on hundreds of thousands, sometimes millions of noisy samples. It shows that when your supervisory signal is perfectly clean, you need far, far less data.
And then they pushed it even further with BiPS General 7b adding some math-focused samples. That got the average improvement up to plus 8.2 points, hitting state-of-the-art scores for open-source models on benchmarks like MathVista.
The case studies in the paper really drive it home. You can see the base model just hallucinating, right? It relies on superficial numerical patterns. BiPS forces the model to attend to the precise structural alignment, the cross-plot relationships, the things you actually need for correct quantitative reasoning. It stops the model from guessing and forces it to confirm.
So to synthesize this whole deep dive, BiPS really tackles the VLM perceptual bottleneck head-on. It defines where to look and what to rely on directly in the training phase, using this clever bidirectional KL constraint system. And it's all anchored by these programmatically synthesized views, which gives you a robust model with zero inference time latency.
The relevance for you, if you're deploying VLMs in fields that rely on detailed visual data, finance, science, medical imaging, it's immediate. BiPS offers a clear path to making sure your model's reasoning is actually anchored in the visual details, not just clever text-based guesswork.
Which brings us to a final provocative thought.
Yeah.
We've seen that programmatically encoding perfect visual evidence into the training signal using semantic code-level control is vastly superior to just crude pixel-level augmentation. So could this programmatic data generation pipeline, this shift from low-level augmentation to high-precision semantic control, could this become the new frontier for synthesizing high-quality, specialized training data across all multimodal domains? It really seems like this approach could hold the key to building specialized models that are both hyper-accurate and incredibly data efficient.